Now we just talked about how to do stubs by calculating them using the tangent or cotangent equation, but we can also use the Smith chart to calculate them. We know that if we have a short circuit, Z of a short circuit is 0, and that point is right here. That's Z of a short circuit. Z of an open circuit is infinity, and that's right there. Let's draw a picture of either our short-circuited case or our open-circuited case, and we can see that this is the load for a stub with a length L and a characteristic impedance Z0. So if I knew that I wanted to have some imaginary part right here, all I would need to do is start at my short circuit and rotate towards the generator, right here like this, and look, I can reach virtually every imaginary part on this transmission line starting with my short circuit. The same thing happens with ZOC. Rotating towards the generator, I'm able to reach virtually every imaginary value. So all I have to do is change the length of the line, and I will be able to create an imaginary component of any size that I want. So here again are the steps. Here's my load, ZL. And let's say that ZL is 100 plus J 100 ohms on a 50 ohm transmission line. So I'm going to plot 2 plus J2. Here is the real part of 2. Here's the imaginary part of 2. There's my Z load. I'm going to draw a line out from the center through my point like this because I'm going to use that to tell me how far I want to rotate a distance d. Remember that distance d is going to match the real part. What that means is when I get right here to point A, I want the real part to be 50 ohms. So ZA, I want it to be 50, and I don't care what the imaginary part is yet because I'm going to use a stub to remove it. If I normalized this by 50 ohms, this would be 1 plus J and some imaginary value. I know I didn't change this because x was some random value before. When you divide it by 50, it's just another random value. So ZA is 1 plus JX. Now if I want to be able to get to that value, it means that I'm going to be on the part where the real circle is 1. This is sometimes called the matching circle. I'm just going to draw a circle. It's always the same one. That's where the real part, every place on this circle, is equal to 1. So if I started at my load and I rotated towards the generator, I should be able to reach a couple of points that represent the real part being matched. Now I could use a protractor and draw a circle right around like this. Put the center of your protractor right there at the center. Put the pencil of your protractor here and start drawing around. But I don't usually have a protractor with me, so I'm going to do the same thing I've done before, which is use a piece of paper, mark this distance, and then I'm going to line it right up here on the center of the Smith chart, and with my straight piece of paper, like this, I'm going to mark right there. That point is ZA. Well, if I kept going around, there would be another point that would happen over here on the Smith chart, right about there. So I'm going to do the same thing. Again, take your piece of paper, put it at the center. I'm kind of going to sketch my paper so you can see it here. Right there is the point, is another possibility for ZA. So here's ZA1, that's the first one I would come to. Here's ZA2. Both of those will give me viable matching networks. They will give me different lengths of line and different distances, but both of them will work. So what I'm going to do is rotate ZL until it gets to, let's do ZA1. Draw a straight line out here from the center through ZA1 and read off the value. It's about 0.32. Then this distance D here is going to be equal to 0.32 minus 0.21. So D equals 0.32 minus 0.21 wavelengths.